Okay, so we're just starting with a bit of Year 1 proof revision. So the first one, so I'm talking for the camera now. For the first one, 3 consecutive integers could either be even, odd, and even, or odd, even, odd. There's no other combination, so I'm going to try that scenario and that scenario. You could argue it was a little bit easier maybe to call the middle one 2n plus 1, or anyway, there you go. And it's the product, so I've got to multiply those together. Proof by exhaustion means try all the different scenarios, which nearly always means odd or even, although I have seen one where it was a multiple of 3, 1 bigger than a multiple of 3, 1 or 2 bigger than a multiple of 3. Okay, so with the even, odd, even, we get this. Remember, you've got to finish it off by, if we're trying to show it's even, so you just need to write it as 2 times something. And then just say which is even as required. So even though you could pull out a 4, we don't pull out a 4, we pull out a 2 because we're just trying to show it's a multiple of 2. And you do the same thing here. You write which is even as required. So did you find a number that didn't work?
And it's 8.
8. And why did you just try all the numbers up to 8, or?
Yeah, just in my head.
Right. Yeah. So 64. When n is 8, you get 64. Take away 8. Take away 1. So it's 56. Take away 1 is 55, which is not a prime number. Very good. Yeah. Yeah. Yes, George.
You have to demonstrate that inside the brackets would be an integer.
Well, you don't need to demonstrate that because n is an integer to start with. I suppose what you need to say is let n be an integer, and therefore 2n is an even integer. So there's no way that can't be an integer.
It's just like obvious.
Yeah. So yeah, I mean, you don't. I mean, it's a good question. It's worth asking, but yeah, you don't have to explain it to death. You know, you can. Right. Yeah. So rational number questions. Rational number is any number that can be written as a fraction. So let's say A, B, C, and D are integers. So you've got one rational number, which is A over B, and another rational number, C over D. Now, if I was going to subtract those 2 rational numbers, I would need a common denominator. Now, if we assume that there's no common factor here, my common denominator would be BD. Those 2 denominators multiply together. To turn this fraction into a denominator with BD, you would have to multiply top and bottom by D, and on this side you'd have to multiply top and bottom by B. So Matt, how can I demonstrate that that is a rational number?
Because A, B, C, and D are integers, so the top and bottom is supposed to be integers.
Yeah. If A, B, C, and D are whole numbers, are integers, then there's no way that sum can give me a non-integer answer. You know, subtracting integers is always going to give you another integer. If that was a division, that would be different. And I know this is a division, but all we're trying to prove is that it's irrational, is that the numerator is an integer and the denominator is. Similarly, b times d, if b and d are integers, then they have to be integers. I would say both numerator and denominator are integers, therefore the answer is a rational number. So rational number questions, I always think they're a little bit weird, but they're never hard. You know, it's just about, I mean, there's a proof by contradiction involving rational numbers, which is just you know, easy peasy. It's just a little bit weird. I'm going to accelerate this a little bit just to get through it. Aidan, how can I prove this is always positive? What would a good first step be?
You could complete the square or use the discriminant.
Right, yeah. But what I do to start with is I prove that it's never equal to 0. And I've got two ways of doing that. I can complete the square and use the discriminant. Now, what we're doing is we're sort of thinking of this in the context of a graph. So I might start my answer to this by saying, well, I'm going to think of this in graphical terms. So I might say, consider y equals x squared, minus 8x minus 12. And I've got the two ways of doing it. I can either complete the square, so that's x minus 4 squared minus 16 plus 20. So that's x minus 4 squared plus 4. And sketch it. And I could say the graph never crosses the x-axis, so y is always positive. Therefore, I've been considering it as a graph, n squared minus 8n plus 20 is always positive. So that's one way of doing it. And the other way is to use the discriminant. So Aidan hit both ways of doing it. The other way is to say, right, when does this graph equal 0? I'm looking for the roots. Where does it cross the x-axis? So b squared minus 4ac would be 64 minus 4 times 1 times 20, which is negative. Therefore, the graph never crosses the x-axis. It hasn't got any roots, so y is always positive, and that means that this is always positive. Now, what would happen if you didn't write consider y equals and just went into this or this using n? I think you'd be all right. But I think it's worth just being, I think clarity is important, just worth being clear. I'm solving what is a quadratic question by considering the graph. And if you do that, make sure you bring it home here at the end by saying, therefore, n squared minus 8n plus 20 will always be positive. I won't do the last one, but if you do the last one, hopefully you will get something that can be factorised with a 2, and that's that. So that's all year 1 proof, and variations of that. Sorry, that's not us. Variations of that are very common. So what we added in year 2 was just one method of proof, and that was proof by contradiction. So I want to revise proof by contradiction. There are two standard proofs that we need to do, and then there are some non-standard ones. And the exam, the syllabus, the specification says exactly that. It says use proof by contradiction, and it specifies these two examples, and then says as well as unfamiliar scenarios. And those of you that have done the proof revision questions will have met some of those unfamiliar scenarios. So the first one that we're going to do is the proof that there are an infinite number of prime numbers, okay? Which was this brilliant proof that Descartes first came along with, and
who's paying him to do that? Like,
who's paying Descartes?
A university or?
Was it Descartes or was it even older than that? Was it Euclid? I think it was Euclid actually, wasn't it? It was Greek. Yeah, I think in those days they probably didn't sort of have. He would have had a benefactor, so you would have had a rich person who would have supported your work.
Could be one of those things where like loads of people around the world discovered it like independently, kind of like pi or.
Well, the classic example of that is sort of the maths of calculus, which was sort of separately sort of defined by Newton and the German guy. Leibniz. Thank you very much. Yeah, thank you.
Also, Japan discovered Pascal's triangle and stuff like that. It's roughly the same time.
Right, there we go. Okay, so we're going to use proof by contradiction to prove that there are an infinite number of primes.
So is this just like a copy and paste sort of?
Yes. They're called primes because if you call them prime numbers, that's a sentence with the number of word number in it twice, which doesn't make sense. They're an infinite number of primes. So what we do with proof by contradiction is we assume that there are a finite number of primes. We assume the opposite. So let's give them a name. Let's call them P1, P2, P3, up to Pn. And do you remember what Euclid did? What was the first step in his proof? He multiplied them all together. So let's let big M equal P1 times P2 times P3. So what you've got here is a number that is in every times table. So, our first prime number is 2, so this number is in the 2 times table. Second prime number is 3, so it's in the 3 times table. It's in the 5 times table. It's a multiple of every prime number. Okay? Sorry? We're assuming there are a finite number of prime numbers. So it's the biggest prime number. 37. 37 is the biggest prime number. Okay? So what I've got here is a number, m, which is a multiple of 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and 37. Okay? And then we consider and it's just genius, isn't it? If you take a number that's in the 2 times table and add 1 to it, it's not in the 2 times table. If you take a number that's in the 3 times table and add 1 to it, it's not in the 3 times table. If you take a number that's in the 5 times table, add 1 to it, it's not in the 5 times table. It's also not in the 4 times table because it's not in the 2 times table. So what we've got here is either a new prime number, or our original list wasn't complete. Okay, so either we found a new prime number or our original list wasn't complete. Now I guess what I'm saying there is the same thing, isn't it? I'm saying the same thing in two different ways. But n plus 1, this is not divisible by any other number. We've just shown that, apart from 1 in
Why
itself.
can't it be divisible by a number that's not a prime number?
Well, but
Because you've added 1.
go on, give me an example.
I don't know, because it's probably like in the billions, but like if you add 1, it could now be divisible by like 8 or.
Well, no, you see, because it's a multiple of 2, so it's also a multiple of 4, and of 6, and of 8, and of 10, and of 12, and of, so add 1 to any of those multiples, and you'll get a number that isn't a multiple of whatever. It's a multiple of. It's not a multiple of 3. Sorry, this is a multiple of 3, so it's also a multiple of 6 and 9, and so it's genius. It's not divisible by any number apart from 1 in itself. And I'm going to double check the wording because I want to make sure I get this correct. So it is either a new prime number or it is it's a product of, or it's a prime number, or it's a product of some other prime numbers that aren't on the list. So right, okay. So I'm gonna say so. So therefore, it is a prime number, or so it's not the same thing. I've either discovered a new prime number, or my list wasn't complete. There were prime numbers bigger than 37. So it is a prime number, or it is divisible by a prime number not in my original list. Either way, I found another prime number. Either this or my original list wasn't complete. So
You mean like bigger than?
So
you mean in that little gap?
it's either a prime number. No. There's certainly nothing in that gap there. But this number might be divisible by a prime number that should have been over this, or itself it might be a new prime number. And because that will be true. So I say right, there's a new prime number. I'll add it to the list. You go through that process again. Add 1. You get a new prime number. So therefore, there are not a finite number of prime numbers.
You said something like Pn is if Pn was the largest prime.
Largest prime that we know about.
Yeah, then you can always generate another one.
That's the whole point. Yeah.
Sure, if it was divisible by a number bigger than the list, then it would then make that number not a prime number and add 1 not a prime number. So
No, if there was another prime number in the list, then there's another prime number. I'm not saying it's divisible by another number not in the list. I'm saying it's either divisible by a prime number that isn't in the list, or itself, if we've got a complete list of known prime numbers, itself is a prime number. I mean, the thing is, you can't think about it too logically because it's not working, is it? This isn't a complete list because we've just found a new one. So it's sort of that's the thing about proof by contradiction. You're assuming something and then showing that you are wrong. Right, the other standard one, which is a bit weirder. I mean that's quite elegant, and I think I've been quite careful about my wording, but I think you'd get away with a slightly shonkier version of that wording. I don't think you need to be too anxious about the wording. It's the fact that you are listing the known prime numbers, you are finding their product, and you are adding 1. I mean that's the key sort of 3 steps, isn't it? List the known prime numbers, find the product, add 1, new prime number. So the second one is to
Why do you have to say that Pn be the largest known prime number?
Okay, I suppose what we're doing here is we're doing it wrong. So no, Pn is just so that is my list. I'm assuming. So no, you're right. I'm assuming that there are a finite number of primes, which is this list here. Now, we all know that's a false assumption, but that's what I'm assuming. So I'm assuming that this list stops at 37.
I don't think you have to say no. You can just say like,
Yeah.
assuming finite. Right?
That's- yeah,
Says a lot.
It's just the last. Yeah. With proof by contradiction,
Yeah.
how can you identify that it's? Would you ever get like a non-copy and paste of proof by contradiction?
Yes. And you've met a couple in that work you did over Easter, and I've got a couple of them now.
Okay.
But let's do the other standard one that's mentioned in the syllabus, which is prove that. And actually, how do you know it's a contradiction? I don't think I've ever seen a question that says doesn't say prove by contradiction. Okay, so prove by contradiction that square root of 2 is irrational. So it can't be written as a fraction. So what do? We assume the opposite. We assume that root 2 can be written as a fraction. And this next bit is important, where A and B are non-zero integers, so obviously an int. And that's its simplified form, so with no common factors. That's a key bit. So A and B, A over B is the fraction written in its simplest form. And this is another copy and paste one, and I think this one is a little bit harder. So this is a good one to sort of drill. Multiply both sides by b. Now I've been quite careful to be clear that the b isn't under the square root sign. So I've sort of exaggerated that gap there. Now I'm going to square both sides. Now this side just gives me a squared. If I square this, I get that squared is 2, and b, I get that. Now that tells me that a squared must be an even number, because it's 2 times something else. And any even square number will have come from an even number. You can't square an odd number and get an even answer. So if a squared is even, a is even. So because of that, I'm going to replace a with a different variable that indicates its evenness. K squared, 2 times 2 and k times k is that. And now I'm going to half both sides. So look, I've shown that b squared is also even. And that means that b must be even. And can you see where I've hit the problem? And this is what proof by contradiction does. You start off doing algebra until you hit a mistake. I said up here that this is a simplified fraction. So a and b have no common factors. Therefore they can't be even, both of them, because they'd be divisible by 2. But a and b have no common factors. So it's broken. We've hit a problem, which is great news. That's what we want with proof by contradiction. So therefore, you can say that, meaning root 2 is irrational.
Would you need to explain that they would do you need to say they have no common factors, but if they're both even, then they'll both be divisible by 2?
Well, you could say, so they can't be even, couldn't you?
They can't be, well, I guess one could.
One could be even, they can't both be even. Yes. So those are the two standard proof by contradictions. Now, proof is mentioned on paper 1 and paper 2, so that tells me that there's going to be a proof by contradiction and a year 1 proof. Which way round, I don't know. But, you know, I do not believe they will have proof questions on both papers and not have a proof by contradiction in there somewhere. So the syllabus says proof by contradiction, including proof of infinitely many primes and the irrationality of root 2, plus unfamiliar context. So that means non-standard textbook cut and paste examples. So here's an example of an unfamiliar one that, you know, isn't sort of a standard textbook one. So there's the reference to proof by contradiction. So we know that we're going to have to start this by proving that the opposite is true, or sorry, assuming that the opposite is true. So we're going to assume that and P and Q are positive integers. Now there's something which crops up again and again here, and if you can recognise it, then you're sitting pretty, and if you can't recognise it, you've got a problem. George, what can I do with that expression?
Square root.
It's not square rooting, because I can't just say 2p minus q. That's not what you get. I can factorise it though, and it's a special case factorisation, isn't it? It's a difference of 2 squares. So, you know, if it had said x squared minus 9, I'm sure you would have all recognised that's x plus 3, x minus 3, because that's something squared and that's something squared. That's why it's called the difference of 2 squares. This is the same. This is 2p times 2p, and that is q times q. So and of course, if you weren't able to see that, you're going to get 0 marks on this, which is a shame. So look out for difference of 2 squares which look a little bit unusual. Now,
what about saying P equals Q?
P equals Q. So to what end?
I don't know, could that work? Because then we could solve it.
No. Now, at this point, we have to introduce a bit of common sense. Remember, we said at the beginning of the lesson, towards the beginning of the lesson, if P and Q are integers, then that's got to be an integer. And that's got to be an integer. So what we're doing here is one whole number times another whole number and making 25. Now there's only certain ways you can make 25 with whole numbers. You can either have 5 times 5, or 1 times 25, or 25 times 1. Now, tell me this, Jacob. Which of these is bigger?
The left one.
So if it's 25 times 1, then that would have to be the 25. So we've got two scenarios. We've got this scenario here, where 2p plus q has to equal 5, and 2p minus q has to equal 5.
Can q not be negative? Are we assuming that?
Q, it says in the question, positive integers. And here we're saying 2p plus q would equal 25, and 2p minus q would equal 1. Now we need to try and solve those two simultaneous equations, which your calculator will do, or you can, it's not a complicated one to do. I'm going to ask what's changed going from one to the other. And what we're hoping is that we'll find that p and q are not positive integers in those two scenarios. So in both scenarios, and these are the only scenarios where an integer times by another integer can give you 25, knowing that they are positive, and we know that they are, it's got to be two positive numbers, because there's no way this can be negative, and so that can't be negative either because the answer is positive. But in both scenarios we get non-integer answers for one of the two variables.
There should be 3 scenarios.
What's the third scenario?
Like the other brackets, 1 and 25.
No, because that is obviously a bigger number than that, if p and q are positive integers, so it can't be 1 and 25, can it? That first bracket has got to be bigger than the second bracket. There's no way it can be the other way around.
So can you just rule out 5 with 5?
No, because q could be 0. Well, yeah, I suppose yes you can, because if you're saying positive integers, that really should rule out 0. Yeah.
If there wasn't the 2.5, let's say it was p and as 3 and 0, would you say that breaks the rule?
Yeah, yes, because I guess yes, because 0 is neither positive or negative. Yeah. So what we'd have to finish it off by saying, but p and q are positive integers. So 4p squared minus does not equal 25 as required. So here's our second unfamiliar context, not part 1 but part 2. We're using proof by contradiction. We are being asked to show that m is even, so I'm going to assume that m is odd. So I'm going to define some integer n. So 2n plus 1 is my odd number. So I'm going to replace m with 2n plus 1. Could use the binomial to expand this, of course. That'd probably be quicker, wouldn't it? So when I expand that, not forgetting to add the 5, I get 8n squared plus, 8n cubed plus 12n squared plus 6n plus 6, which is an even number. But we're told that actually that's odd. However, n cubed plus 5 is odd. So it hasn't worked. Therefore, m can't be odd, and if it's not odd, it must be even.
Do we say 0 is even?
Sorry again, sorry?
Do we say 0 is even?
Well, yes, yes. In order for the pattern to work, that has to be, because it's 2 times 0, isn't it? Good stuff.